Now that we have inserted a freewheeling diode in our circuit DM, so now this is providing a path to the discharge of energy that was being absorbed or was developed across this inductor in the forward biased condition. Previously, it has to force to increase the conduction angle of this diode D1 for the release of energy. But now we have inserted this DM, due to which uh, now we have this path for the release of this energy. That's why the conduction angle of this will be now from 0 to pi, and whatever the discharge of the energy, it will take place through this diode, freewheeling diode DM. Consider that we have this AC voltage source, our diode D, and a resistance of 1 ohm and a 10 millihenry inductance. The voltage across these resistors is denoted by VR, and the voltage across this inductor is denoted by VL, and the collective voltage across these two will be output voltage V0. So this is the phase shift that I was talking about, that will be between the Vs and Vr due to the insertion of an additional inductance in our load. So you can see that there is a phase difference between this Vr and this Vs. Now the voltage waveform across diode. So consider that the area, this area denoted by this yellow color is area A, and this with purple color is area B. Vs is the supply voltage, Vr is the voltage across the resistor, and Vd is the voltage across the diode D, in case when there was no freewheeling diode. So you see that the conduction angle of this diode has increased up to this point, to the point until when the inductance completely releases its energy. Only then this diode D goes into the reverse operating condition, and now the voltage will appear across this diode D. The voltage developed across this inductor VL will be Vs minus Vr. That is the difference of this area minus this area. So by doing that, Vs minus Vr, the value of inductance VL will be something, the waveform across the inductor will be something like this, shown here in the green color. By subtracting the area A minus B, we can find out this voltage waveform across the inductor VL. Now considering the second case in which we have used this freewheeling diode DW. But before going into the analysis of this circuit in which a freewheeling diode has been used, let us first define that what are freewheeling diodes. It is a diode that is connected across an inductive load in parallel to prevent the development of any negative voltages across the switch. DW here is the freewheeling diode. When the current in the circuit suddenly drops to 0, this may be due to the fact that this diode D has gone into the reverse biasing condition, or let us consider that I have some switch S in series here that I opened at time instant let's say t1. So due to which the current the current in our circuit will suddenly drop to 0. But what will happen by this sudden change in the current? Huge voltages with reverse polarity will appear across the diode D. It is due to the fact that we have an inductor in our circuit, and this inductor does not allow the change of the current change of current to happen very suddenly. It will always oppose the change of current. So what are the issues associated with the development of these high voltages in reverse polarity? The issue is that they may damage the diode depending upon the peak inverse value of this diode D. When the freewheeling diode is used, the energy from this inductor can now pass through this diode rather than forcing this diode D. So this is like this diode is known as freewheeling, for its provide a path to the release of this energy from the inductor that is dissipated through this resistor. And I remember asking a student from me in lab that why is that there are some diodes attached to the MOSFET while we were developing the half bridge or the full bridge in lab. A student asked me that why are there some diodes attached to this switch. The reason is same. These switches are also diodes are also freewheeling diodes. Since we do not know what kind of load we are dealing with, for example, if we are dealing with an inductive load, in that case these diodes are necessary to be placed in our across these switches in order to prevent these diodes from these high voltages that will appear across this switch due to an inductive load. This inductive load may be a motor or some other load. So I think now it is clear that why in some of the circuits that you found online had these switches across them in parallel. They are also freewheeling diodes. When the switches will turn off and the load current will suddenly drop to 0, IL will suddenly drop to 0. The energy stored by this motor or any other inductive load, this now needs a path to be delivered safely, to be dissipated. That's when these freewheeling diodes will provide it a path to safely discharge or dissipate this energy and save the switches from damage. This is the waveform that is being developed across the diode resistor in case when freewheeling diode is attached. You see here that the diode, the voltage across the diode is now again the negative half cycle of the AC signal. That is similar to the case when we were using a resistive load. But see that the average value of the voltage across this inductor has increased as well. If you see, previously it was going towards the 0 crossing, but now it has some average value that is greater than 0, and also see that this tail has also increased as compared to this, because previously this has to enforce through this this source, and some of the it has to oppose against this source, and some of the charges could be lost in the way and the power could be dissipated in this source. But now the current is passing through, or the energy passing through this path, where it has no kind of dissipating element